Let's look at another example right here. This was the first example that we looked at. So let's see. If we start, so it's always a good idea to start where the slope of the tangent line is 0. So as you can see, this is one of the cases where the slope of the tangent line is 0. We also can see two other spots, the same thing happening, right? So right here, the slope of the tangent line is 0, and right here as well. So let's see, this is approximately negative 1.5, and this is 0. X is equal to negative 1.5, x equals to 0, and x equals to positive 1.5. So let's draw this or transfer these points onto the graph of f prime of x. So first one is 0, 0, right? So we have 0, 0. So at 0 seconds, or x equals to 0, our slope is equal to 0. That's why we have this point. Now another point where slope is equal to 0 is at x equals to negative 1.5. So we will put at negative 1.5. We will also put a dot at 0. Another point is right here. When x is equal to positive 1.5, the slope of the line is also 0. So on the graph of f prime of x, we will also put that point 1.5 comma 0, 1.5 comma 0. This one is 0 comma 0, and this one would be negative 1.5 comma 0. So again, remember, these y values are the slope of the tangent line of the f of x. So now from this 0, right, from here to here, we are starting increasing, right? So as we continue taking looking at the points, right, until probably here, we see that the tangent line, let me make it bigger. We see that at this point, the tangent, the slope of the tangent line is increasing more and more. And then as we kind of go over this x-axis, the slope starts a bit decreasing until it reaches 0. So we can say that right here, the slope is the maximum, right? It's approximately, I would say it is approximately 4. Okay, so from this 0, we reach until 4, and then we start decreasing again until we reach 0 here. So let's transfer that to our f prime of x. So between this negative 1.5 and 0, we are somewhere in between, maybe a bit before negative 1, right? So it's 0.8 probably. So a point here, 0.8, and we're reaching 4 here. So that's going to be a point right here. So the slope of the tangent line here is 4. Now, as we go from this point from here to here, you see that the slope here is kind of increasing, decreasing, and it's kind of in magnitude, it's pretty big here, right? But with the negative sign. So we are continuing this in this manner, right? So we have the kind of like this, and then something like this. So as you can see, at this point right here, the slope is smaller than at this point, right? It's gonna be the maximum somewhere again at 0.8 probably. And then it starts decreasing again. So the slope right here of the tangent line is smaller than right here. So if we extend it, that's going to be going this way. For this one, it's going to be going this way. So the slope right here is more large, right? But with the negative sign. So it's in magnitude, it's going to be larger than this one. So we say that at positive 1.8, the slope is approximately negative 4, right? So let's transfer that point onto our graph. So we have 0.8, and the point is -4 approximately. So it's going to be somewhere here. Okay, now let's look at this end behavior. So what's happening on the right side? As we reach minimum here, slope of the tangent line is 0 here. As we take more points, we see that the slope of the tangent line starts increasing until it's almost a vertical line. So what does it mean? When it's a vertical line, that means that it's kind of going to that infinity. When x is 2.3 approximately, our slope, the slope of the tangent line is almost infinity. So we can transfer that point onto our f of x graph. So at point approximately 2.3, somewhere here, the slope is gonna be very, very, very big, right? It goes to infinity. So we can put, let's say I put a point somewhere here. It doesn't really matter because we're shooting that to infinity. And now same goes from the left side, right? So if we take a point somewhere here, you see that the slope here is very, very negative. So the magnitude is very large with the negative sign. So if we pick a point, let's say -2.3, the same, -2.3, we see that the slope of this tangent line is very large and negative. So I can transfer that to my graph. So at -2.3, my slope is very large with the negative sign. So in magnitude is very large. So now I can just connect all of these points and see what happens. Okay, the best as I could, I created the function of a graph of a derivative of the function f of x. This is what the graph of the derivative would look like. So now let's explore an important relationship between differentiability and continuity. So the theorem states if f is differentiable at a point, then f is continuous at that point. This is a fundamental result in calculus. It tells us that differentiability is a stronger condition than continuity. In other words, if a function is differentiable at a point, it must also be continuous there. However, the converse is not true. A function can be continuous at a point, but not differentiable there. And there are several situations where a function might be continuous but not differentiable. For example, it could be a sharp corner where the left and right derivatives exist, but they're not equal to each other. And we'll see an example of that a bit later. Then a cusp where the function has a vertical tangent line, or a discontinuity where the function is not continuous and therefore not differentiable. So let me show you several examples of this scenario. Okay, so this is the example of a corner. If we move along the curve up until here, we see that the slope of the tangent line is always constant and it's equal approximately maybe 1, right? So up until we reach this point. And then if we look at starting from this point, the slope of the tangent line is also constant, but it's going to be approximately -1 everywhere. So if we draw a graph of that, what we have essentially is first up until this point, A, so this is where my A is, this is my f of x, and this is my f prime of x. So the slope of the tangent line is +1 here until we reach that A, right? It's always constant. And then after this corner, it becomes -1, right? So you see that we have a discontinuity here in the function, in the graph of the derivative. So that means that we have no differentiability in this case. From the left side, it's a +1. From the right side, it's -1. And at that point, we cannot say exactly is it +1 or -1. We have the kind of a jump here. So let me show you the second example, which is this one. So again, we start moving. So this is my f of x, by the way. Okay, so we start moving. Everything is pretty nice until we reach this 0. So at this point, x equal to 0, we say that the slope of the tangent line is infinity. But can we say exactly, is it positive infinity or negative infinity? It's just a vertical line, right? So we cannot say exactly if it's positive or negative infinity. So in this case, this would be also not differentiable point. And the last example would be the following. Let's say we have a function, and again, we are going along the curve and measure our slope of the tangent line until we reach somewhere here, let's say, and you see that from this side and this side, they are different, right? So here, it's kind of getting higher up here, so the tangent is like this, and on at this point it's changing right away to negative, right? So we cannot say exactly what's going on here. So this jump or discontinuity also prevents us from measuring what the derivative is, right? So that's why we have this theorem, and at these specific cases, the function is not differentiable. So please keep that in mind.